Welcome back to another episode of Game Theory. We're still in Chapter 12, looking at evolutionary games. Let's work through another example. So here, look at the group project game Wilma as a chicken game. So the usual setup, you have you and one other student are working on a group project together. And for the project to be successful, you need at least one person to put in the work. So there are two types of students. There are lazy types, we'll call them L types, and there are responsible types, R types. And if you have two lazy types together, then they both don't work, so they both fail the project. We'll mod as a payoff of minus 100. If two responsible types are in the same project, they both work and the project goes well, we'll call that 0, 0. If you have one lazy type and one responsible type, then the responsible type does all the work and the project goes well. However, they depend on so much effort that the responsible type is overall not very thrilled about this. And if you have a minus 20, the lazy type can play video games all day and still get a good grade. We'll model as a payoff of positive 20 for the lazy type. And it's symmetric. So I'll have PR be a proportion of responsible types. So 1 minus PR is a proportion of lazy types. So we'll go through our three-step process to find what are the evolutionary stable strategies here. So we first find each species' expected fitness. So in terms you're more familiar with, the expected payoff. Just saying for each type, it's one species, but two types. So the responsible type, expected fitness, so with probability 1 minus PR, they meet a lazy type. And if you're the responsible type and your partner is a lazy type, you get minus 20. So we weight that by the probability. Then with probability PR, you meet another responsible type. In that case, you guys get 0. So that's going to just go away. So we're left with 20 PR minus 20. If you expand this out. So it's minus 20 plus 20 PRs made in trade places, so you get that. Now find the lazy type's expected fitness. With probability 1 minus PR, they meet another lazy type. In that case, they get negative 100. So that fitness is minus 100 and multiply it by the probability, and you get that. Now with probability PR, they meet a responsible type. In that case, your fitness is 20. So let's find what that comes out to. So this will be minus 100 plus 100 PR. They have a plus 20 PR. And if you combine like terms, you get 120 PR minus 100. All right, that's step one. We found each type's expected fitness. So next step is we find under what conditions are each type equally fit. So you know there are three equilibria. So there's all responsible types, all lazy types, and a mixture. So we have to try to find what's the mixture. So we said that the responsible types have this fitness, 20 PR minus 20, or that payoff you want to use economic terms. And so the lazy types have this fitness slash payoff. So you have one equation, one unknown. Let's go and solve that. So I'll put the 100 over here. 100 minus 20 is going to be 80. I'll subtract a 20 PR from this side and throw it over there. 120 minus 20 is going to be 100. Divide both sides by 80. Divide both sides by 100, and you get PR is going to be 4/5. So that is when each type is equally fit, or in our biology terms, that's the polymorphism. In economic terms, that'd be the mixed strategy Nash equilibrium. We're not done yet. So in biology, you also have to analyze the stability. In economics, you have to find equilibrium, that's it. But biology has this extra condition of stability. So let's see. So put fitness over here and PR, proportional responsible types, out here. So for the responsible types, the fitness level is 20 PR minus 20. So that means that their intercept is negative 20. That's going to be down here. Wait, I better draw it different because I have an even more negative intercept over here in my next step. So let's put that up somewhere. Wait, I'll just recycle that point. I'll call a point minus 100 for my next step. I'll put the minus 20 up here. All right, so the slope for the responsible types is positive 20. So let's say it looks like this. That'll be PR of 1 over here. For the lazy types, the slope is 120, so that's going to be more positive. Let me get another color out so you can see the contrast more clearly. There we go. So that's the graph for the lazy types. We know when they cross over, that's because we established in step 2 that the two types are equally fit when PR is 4/5. So we got a picture. Now let's look at stability. So if we're over here when PR is low, then the responsible types are more fit. So responsible types fitness is up here, lazy types fitness is down there, so responsible types are fitter. That means that the proportion of responsible types will then increase. So I'll draw arrows showing PR going up. So again, fitness being higher means that you're going to live more, you're going to live longer, you're going to pass in your genes more, be able to reproduce more. So that's why PR rises when R types are fitter. Now on this side over here, the L types are fitter. So here's the L types fitness, there's the R types fitness. So if the L types are fitter, that means they're going to reproduce more and the R types are going to die off. So proportion of R types will then decrease. So I'll draw arrows going in the other direction from this side. So we have the stability for the 3 equilibria. So there's the PR equals 0 equilibrium, a monomorphism, because all species are the same type. That one is going to be unstable. That's because we have PR being 0 over here. The arrows you can see are going to pull you away from that. So if PR were to rise a little bit above 0, it's going to keep going up. So that can happen if, say, there's a mutation, or the term is if the population gets invaded by a mutant. So if one R type gets in there somehow, or if one R type migrates from another area, then R type is going to proliferate, and it's going to push you away from that initial equilibrium. So if PR rises a little bit, you don't go back where you started. Instead, you're going to rise even more. That makes that equilibrium unstable. So the next equilibrium is the PR equals 4/5. That's a polymorphism because now there's more than one type. Some are R types, some are L types. If PR were to rise a little bit above 4/5, the arrows push us back to 4/5. If PR were to fall a little bit below 4/5, the arrows push us back to 4/5, so that one's stable. So we call that an ESS, an evolutionary stable strategy. Because if you deviate a little bit from the equilibrium, you end up going back to the same equilibrium. The last equilibrium to analyze is what if PR equals 1. That's another monomorphism because now all the type all species are the same type. They're all responsible types. So we start at PR being 1, and we go down a little bit. The arrows push us further down towards that 4/5 point. So that's going to be unstable. If you deviate from where you start, you end up going somewhere else. You don't come back to your initial equilibrium. So in this case, unlike our earlier examples, the only stable outcome is when you have a mixture. You have a polymorphism. Earlier, we had the other examples with the prisoners limit game and the repeated prisoners limit game. The only stable equilibrium is where everyone was the same type. So it is possible to have stable polymorphisms. And there is some intuition for what's going on here. So if you think about our game, if everybody's an L type, then everyone's going to be failing. That's not going to work very well. So that's not going to be stable. If everyone's an R type, then you could add one lazy type to our population, and that lazy type is going to start getting 20 instead of 0, so lazy types should proliferate. That means that the all R types equilibrium is also going to be unstable. And again, you can verify the similarities and differences between this biology concept and economic game theory. Let's find our Nash equilibria using our typical best response analysis. So your opponent plays L, your best response is R. If your opponent plays R, your best response is L. If your opponent plays L, if you're playing L, your opponent's best response is R. If you play R, their best response is L. So it's a chicken game that there are two Nash equilibria, but your interests are at odds with each other. So you prefer one Nash equilibrium, your opponent prefers the other. And if you do some work, you can verify there's also a mixed strategy Nash equilibrium, where PR is 4/5 for each player. So each of those Nash equilibria, what am I trying to say? The mixed strategy Nash equilibrium, PR equals 4/5, is evolutionary stable. Whereas each of these equilibria over here are not stable. That shows once again that every ESS, every stable under evolution strategy, is a Nash equilibrium. Not all Nash equilibria are evolutionary stable. So that wraps up our chicken game version of the group project game. Come join us for our next episode, and we look at a game where there are two different species interacting with each other.